In this video, we're going to take a look at some vocabulary for the atomic structure unit of Advanced Chemistry 30S. We'll look at how to apply this, and then we're going to take a look at a topic called mass spectroscopy and average atomic mass. So some basic terms that are very important ideas. One is the idea of an atomic number. It's given a symbol which is a little strange. The symbol for atomic number is the capital letter Z. When you're looking at atomic number, you're counting the number of protons that are in the nucleus of an atom. So there's the definition of atomic number. It's the number of protons in the nucleus of the atom. Now, if the atom is neutral, and this is not always true, atoms are not always neutral, but if the atom is neutral, then the number of protons and the number of electrons would be equal. So therefore, the atomic number could also indirectly tell you the number of electrons. Don't define it as the number of electrons. The atomic number is the number of protons. But in a neutral atom, it will also be equal to the number of electrons orbiting the nucleus. It's the atomic number which determines the identity of the element. So if you glance at a periodic table, you'll see that each element on the table has a unique atomic number, and that atomic number is stated on the periodic table. For example, you'll see a box for hydrogen on our table. It'll have the symbol H. It'll have a number 1, and then below the symbol a number 1.01. The number 1, the whole number, is the atomic number, so that's Z. If you looked up carbon on the periodic table, you'd see the symbol C with the number 6 above it and 12.01 below it. The number 6 is its atomic number Z. So a carbon atom is carbon because it has 6 protons in its nucleus. That is what identifies the element as carbon. Hydrogen, every atom has 1 proton because the atomic number is 1. So atomic numbers are found on the periodic table above each element. Another important term is mass number. Now notice both of those pieces of vocabulary include the name number, and that's because in both cases we're counting something. In atomic number, we were just counting the number of protons. In the mass number, we're counting now the particles that give an atom its mass. The mass of an atom is almost entirely found in its nucleus, so we're counting now the number of protons and neutrons. Sometimes, because they're in the nucleus, they're collectively called the nucleons that are found inside the atom. You will never find a mass number on a periodic table. Okay, they're not found, and that's because there are different isotopes of atoms. Okay, isotopes is our third term. The definition here, atoms of the same element, or atoms with the same number of protons, or atoms with the same atomic number. You could have said any one of those three things, that have different numbers of neutrons, therefore different mass numbers. Okay, so those are different ways of defining isotopes. So atoms of the same element with different mass numbers. So therefore, when you look at an element like hydrogen, it turns out that there are 3 different common isotopes of hydrogen, each one with a different mass number. For that reason, you're not going to find mass numbers on the periodic table, because for hydrogen you'd need 3 different mass numbers shown in that one little box. It would just be too crowded. So the atomic number Z is the number of protons in a nucleus. The mass number, capital A is its symbol, is the number of protons together with neutrons. Isotopes are atoms of the same element that have different numbers of neutrons, or different mass numbers. When we say carbon 14, the 14 behind the name carbon, this is the mass number. And now I'm talking not just about carbon, but about the isotope carbon 14, the atoms of carbon with that particular mass number. This tells me that there's 14 protons and neutrons inside that isotope of carbon. A last common term is atomic mass, not to be confused with mass number. The atomic mass is exactly what it sounds like. It's the mass of the atom. If you had a balance, an electronic balance sensitive enough, you could put an atom on that balance and imagine reading on the balance what its mass is, in the same way you'd find the mass of a graduated cylinder or the mass of a rock. Because it's a mass, we expect that the number here is going to be ugly. It's not going to be a nice whole number. It's going to have a decimal with it. Okay? The units can be measured in grams. That would be a common way, or kilograms. But in chemistry, we often talk about the mass of atoms in special units called atomic mass units. Atomic mass units we'll talk about later. They're abbreviated AMU. Talking just a little bit more about isotopes. Here is an example of 3 different isotopes of hydrogen, and you're expected to know these names because hydrogen is pretty common in chemistry. Its isotopes have unique names, and that's a little unusual. The most common isotope of hydrogen would have 1 proton in its nucleus, so there's a proton, P, with 1 electron orbiting the nucleus. Now just ignore this little dotted line here. I'm not sure why the graphic shows that. There's a proton as a nucleus with an electron orbiting. That's hydrogen. Now if you want to be more specific, you could call this hydrogen 1, because its mass number is 1. It's got only 1 nucleon, 1 proton as a nucleus. Hydrogen 2 is another isotope of hydrogen, and hydrogen 2 now has not only a proton but also a neutron. Because it's hydrogen, it has to have only 1 proton, but now it's got this extra neutron, so its mass number is 2. Therefore we call it hydrogen 2. Its special name is deuterium. That's a commonly used name for this isotope, which you should know. Because there was only 1 proton, which was positive, there's still only 1 electron, negative, orbiting the nucleus. Remember that neutrons are neutral. The number of protons and electrons will be equal because the number of positives will equal the number of negatives in a neutral atom. The third isotope of hydrogen, hydrogen 3, is sometimes called tritium, and you do need to know that name as well. Now there's 1 proton with 2 neutrons in the nucleus. Okay, and again there's still the 1 electron orbiting, which matches the 1 proton in the nucleus. So these are all hydrogen because they have 1 proton. They're different isotopes of hydrogen because they have different numbers of neutrons in their nuclei. When you look at a slightly different example now, a different way of representing it, we can represent the isotope using this format. I'm going to write it a bit bigger. This is the element sodium. And in this isotope of sodium, its nucleus, which is enlarged here, has 11 protons. If you glance at a periodic table, you can verify for yourself that sodium, Na, has 11 protons. So we're going to write the number 11 on the bottom left-hand side behind the symbol. That's the atomic number, Z. Above it, we're going to write the mass number. This isotope of sodium has 12 neutrons, so this would be sodium 23. 12 neutrons, 11 protons. Its mass number is 23. So we'll put a 23 above the number 11 on the left, and there is a chemical symbol for this isotope. Rather than drawing it, you could represent it with that symbol. The other common isotope of sodium here, Na, still has 11 protons. That's why it's sodium. But now it has 13 neutrons, so its mass number is now 24. This would be sodium 24, a different isotope of sodium. The atomic number Z below, the mass number A above. In the package that you picked up in class, there was a worksheet that's on the second page called Atomic Theory Isotopes. And you should now have enough information to fill this in. I'll just do the first one for you. Its name is, this isotope's name is carbon-14. So if we have a periodic table, you can find carbon and see that its atomic number is 6. So look on a periodic table to get that. The mass number is not found on a periodic table. The mass number is there. So carbon-14, its mass number is 14. The symbol will follow the convention we just used. Carbon is the symbol with 6 as the atomic number and 14 as the mass number, written on the left like that. The atomic number tells me how many protons are in the nucleus, so there are 6 protons. The mass number, 14, meant 6 protons and 8 neutrons, right? If there's 14 protons and neutrons total, and there were 6 protons, then 14 minus 6, there have to be 8 neutrons. 6 plus 8 is the mass number. Okay, one more. The second one's atomic number is 8, so I'm going to glance at a periodic table. That's oxygen. So the name would be oxygen dash, and this guy's mass number is 16, so oxygen dash 16. The symbol would be O with a 16 over an 8, the atomic number on the bottom, the mass number on top. The number of protons is 8, that's the atomic number, and the number of neutrons would be 16 take away 8, so in this case it's going to be 8 as well. So 16 is the protons plus the neutrons, 8 was the protons. If you subtract protons plus neutrons minus protons, you'll be left with neutrons. So mass number minus atomic number is neutrons. You should be able now to finish this worksheet on isotopes. That leads us to the mass spectrometer. The mass spectrometer has a lot of uses in chemistry, some really high-level uses in an area of chemistry called analytical chemistry. In our discussion of isotopes, we're going to look at a simple use of the mass spectrometer. You have on the left, and you don't need to know the fine details of its operation, but in fact in a real mass spectrometer, everything you see here would be contained inside some kind of plastic or metal container. You would never see the inner workings of the mass spectrometer. Inside there's an oven called a vaporizing oven. You'd have a spot on the outside of the spectrometer where you could inject a sample of an element. So in this case we're going to inject a sample of neon gas. That neon gas, if it wasn't already a gas, would be heated, vaporizing until it becomes a gas. The atoms of the gas come out of the oven where they're bombarded, in this case by probably X-rays, and that causes them to be ionized. The X-rays strip away electrons, leaving them positively charged. Now that they're positively charged, we can use a charged grid to attract them, to accelerate the beam of charged particles. These two plates here will focus the beam into a very narrow beam, and then finally we pass that beam through a strong magnetic field. Just like taking a slingshot, filling the sling with a handful of rocks and throwing them all at once, the heaviest rocks would travel the smallest distance. The lightest rocks would travel the furthest distance. So the magnetic field swings and spreads those isotopes out. The heaviest isotopes fall here, the shortest distance. The smallest isotopes fall over here, and we end up seeing 3 different hits on that screen. A computer would display something like this, and this is called the mass spectrum. On the left of the graph is the abundance. The abundance is actually the area under the curve. So we can see in this graph with mass number on the x-axis that the computer is telling us that for neon there's 1, 2, 3 isotopes of neon. One with a mass number of 20, another over here at 22, and a really small amount of this guy at 21. I say really small because the bump there, the little peak, is very, very small. These percentages that you see are called the abundances, or the natural abundances, and what they simply mean is of all the isotopes of neon that were in that sample, 90.92% of them were neon 20. 8.82% of them were neon 22, and a very small amount, 0.26%, were neon 21. So most neon atoms in nature are neon 20 as the isotope. Those abundances, again, are simply the areas under the curves on this graph, the relative areas. Now, what can we do with that information called a mass spectrum? Well, using that information, we can calculate something called the average atomic mass, and this is what shows up on a periodic table. For example, we've got chromium and a table with 4 isotopes of chromium, and for each isotope, the abundance from their mass spectrum. Now notice these are not mass numbers, these are actual atomic masses measured in AMUs, and that's why the numbers are decimals like this. So they're not just mass numbers, which have to be whole numbers. Now if we remember that a proton and a neutron each weigh approximately 1 AMU, and if we remember that electrons are almost massless, then when I see that the mass of this isotope is 49.946 AMUs, I can probably safely assume that its mass number was 50. It has to have 50 protons and neutrons because each proton and neutron weighs 1 AMU. This guy's mass number was probably 52. This guy's mass number is 53. And this guy's mass number is 54. So these would be the mass numbers A. But these numbers are more powerful. Those are the actual atomic masses of each isotope measured in AMUs. And look at all the significant digits in there. Over here we have the abundance of each isotope. So if we know the abundance and mass of each isotope, can we calculate the average atomic mass of chromium? Well, I hope you know some advanced math and that you're pretty clear that the average mass is not going to simply be the average of these 4 numbers. Although these are the masses of the 4 isotopes, they're not equal in abundance. Therefore, the average is not going to simply be the average of those numbers. We're going to have to calculate what you would have called in your math class a weighted average. So let's jump in and try this. So finding the average, I'm just going to zoom in a little bit here. Finding the average atomic mass, make sure you're copying this, the average atomic mass of chromium. And I'm going to use these numbers, the masses and the abundances, to do this. So let's jump in. The average mass, I'm going to just do a weighted average calculation, I hope this makes sense to you, will be the abundance of the first isotope, 4.35%. I'll switch from percent back to a decimal form by dividing by 100, multiplied by its mass, so 49.946 AMUs. So the abundance of that isotope multiplied by its mass, plus the abundance of the next isotope, 83.79 over 100, divided by 100 just converts it back to a decimal, times its mass, 51.941 AMUs. And you just complete that process, continue doing that until you've run out of isotopes. So plus 9.50 over 100 times 52.941 AMUs plus 2.36 over 100 times 53.939 AMUs. Okay, so make sure you understand what we did. We took the percentage of each isotope multiplied by its mass and added them together. That's a weighted average. So to do that on my calculator, 0.0435 times 49.946 plus 0.8379 times 51.941 plus 0.0950 times 52.941 plus 0.0236 times 53.939 equals 51.996. Now, if I'm multiplying here, I've got to watch my sig figs a little bit. 3 sig figs times this, I've got to keep 3 sig figs in here, and 4 sig figs in here, and 3 sig figs here, 3 sig figs here. Then when I add them, I keep the number of decimal places the same as the smallest number of decimal places. That's a little complicated, but if you follow that pattern, you're going to get an answer like this. 51.996 will become 52.00 grams is the average, AMUs, AMUs is the average atomic mass of chromium, and it's a weighted average. If you looked on a periodic table for chromium, you'd see this. Chromium with the number 24 above, that's its mass number, has 24 protons, its atomic number has 24 protons in its nucleus, and underneath it you'd see this number, 52.00, or perhaps 51.996, something like that. That's the average atomic mass on a periodic table. The average atomic mass. Okay? That's not that hard, I hope you'll agree. There's a slightly harder level of question, and that's this one here. And it works when you have just 2 isotopes. Okay, so this works only if there's 2 isotopes. We're going to work backwards. We're told here that naturally occurring lithium has 2 isotopes, and we're told their masses, 6.015 AMUs, 7.016 AMUs. So that must have been lithium-6 and lithium-7. We're also told the average atomic mass of lithium, which we could have found on a periodic table, 6.941 AMUs. Knowing that information, we're going to calculate the abundances of the 2 isotopes. And you can see the answers there, but we're going to calculate those 2 abundances. To do that, I'm going to set it up like a math question. That's what we're doing here. And a very good approach, I'd want to see this on a test, is identifying variables. We have 2 variables. I'm going to say let X be the percent abundance of the first isotope, which was lithium-6. Now I'm going to simplify life for me by saying in decimal form. In other words, if it's 80%, X is going to be 0.8. That way I don't have to worry about dividing by hundreds anymore. I'm going to let Y be the percent abundance of lithium-7, the other isotope, also in decimal form. Now, 2 variables. Your math class, you should be already thinking, this means if we're going to find these 2 variables, we need 2 different equations, and then we're going to need to solve a system of equations. Well, pause the video and see if you can think of the 2 possible equations we could write based on these variables. Alright, did you look at the question and notice we know the average mass, and we knew the mass of each isotope. So one of my 2 equations will simply be the equation for average atomic mass that we used a minute ago. So the equation number 1, my average atomic mass equation would be 6.941 has to be the first isotope's mass, 6.015 AMUs, times its abundance in decimal form. Now, because it's already in decimal form, I'm not going to write divide by 100. Plus the other isotope's mass, 7.016, times its abundance, Y. So there's my first equation. The second equation is a little less obvious until you see it, and then it should be very obvious. Since these are two percentages and are the only percentages, the percentages would have to add together to give 100%. For example, if one was 80% of lithium atoms, the other has to be 20%, since these are the only two isotopes of lithium. But we're not dealing with percentages here, we're dealing with the decimal forms. So 100% as a decimal form is 1. So if I take the two abundances, x and y, they'd have to add up to get 1 as the answer. So equation number 2 is adding the abundances and saying I have to get 100%, which in decimal form is the number 1. Now see if you can pause the video and use your substitution or elimination, use whichever approach you like, and see if you can get these two answers. X is 7.5% and Y is 92.5%. This is the abundance for lithium 6. This is the abundance for lithium 7. Notice the answers look reasonable because the average mass was very close to 7, which means there had to be a lot of isotope number 7 and a very little bit of isotope number 6. So see if you can get those two abundances mathematically, and that'll be the end of this little lesson.